Good day everyone, my name is Ratul Haldar and I have completed my undergraduation from American International University, Bangladesh, and I am pleased to present my work which is multi-architecture deep learning approach for enhanced energy consumption forecasting. This work was conducted under the supervision of Mr. Kazi Firoz Ahmed sir. To keep us focused and on track, here is a quick overview of what I will present today. We will begin by establishing the introduction and motivation, especially why accurate energy forecasting is a critical global challenge. This leads naturally into our research objective and concept, outline the problem we aim to solve. Next, we will dive into the core of our work, which is the methodology and which is the data and pipeline, followed by a deep look at the specific model, architecture, and training we employed, which includes our novel weighted ensemble approach. The most compelling part is the result and performance analysis, where we demonstrate the superior accuracy of our ensemble model. Finally, we will conclude with the real-world impact and future work. Let's get started. Let's begin by setting the context. We face a significant global energy challenge. Critically, the building sector accounts for a large share of global energy use. Therefore, obtaining accurate and reliable energy consumption forecast is paramount for strategically facilitating our move toward carbon neutrality goals. Why deep learning? Traditional statistics forecasting methods frequently struggle with the non-linear, complex interdependencies in modern analysis datasets. Deep learning has proven to be a game changer, excelling at detecting complicated trends and significantly improving prediction capability. Then the research gap we target is the need for comprehensive hybrid and ensemble approaches that strategically combine multiple deep learning architectures to overcome their individual model limitations. Our main objective was to develop a robust multi-architecture deep learning ensemble model for superior short-term energy consumption forecasting. The literature shows that LSTM-based methodologies are effective, and while transformer architecture can be powerful, they show a tendency for overfitting on some datasets. This reinforces the proven effectiveness of ensemble learning, combining multiple models, a strategy validated by the Dasher Great Energy Predictor 3, or we can say GEP3 competition. The gap we targeted was the need for a comprehensive approach that strategically combines this diverse architecture to overcome individual model weakness. With that goal set, let's look at the data we used and how we prepared it on the next slide. We utilized the Azure Great Energy Predictor 3 dataset. This dataset is actually rich, including meter readings like electricity and chilled water, and extensive meteorological features like air temperature and wind speed, and also has time features. Then to ensure robust model training, a meticulous pre-processing pipeline was crucial. We handled outliner handling, then perform missing data imputation using linear interpolation, then created rich features, engineering inputs, and applied min-max normalization. Once the data was ready, we moved to the overall methodology and the specific model architectures. The end-to-end pipeline is a systematic four-step approach for enhanced energy forecasting. Which are step 1, data acquisition and pre-processing, which involves cleaning, imputation, phasor engineering, and scaling of the Azure GP3 dataset. Then the Step 2, which is model training, where we train the individual base models, which are MLP or multi-layer perception, then LSTM or long short-term memory attention, and transformer using optimized hyperparameters. Then step 3, which is ensemble creation. This is our primary contribution, which is implementing the weighted averaging strategy based on the performance of the individual models on the validation set. And finally, evaluation and analysis, where we conducted a comprehensive performance assessment using a set of key metrics such as root mean squared error or RMSE, then mean absolute error or MAE, then R squared, which is the coefficient of determination, and then the symmetric mean absolute percentage error or SMAP, and root mean squared logarithmic error, which is called RMSLE. The base models were the advanced MLP for capturing nonlinear features interactions, the LSTM with attention for capturing long-term temporal dependencies, and the transformer model for capturing global sequence dependencies. Let's look at how we optimize these models and combine their power. Our training used the mean square error or MSE as the loss function and the Adam optimizer for efficient convergence. We also used regularization techniques like dropout and early estimate to mitigate overfitting. Our key innovation is the weighted ensemble model. This technique takes predictions from all three base models, which I have just mentioned, and combines them using a weighted averaging strategy. The weights are optimized based on validation performance, then ensuring that the ensemble capitalize on the complementary strength of each model and to reduce error. Let's see how this ensemble strategy perform against the individual models. The results clearly demonstrate that the ensemble model achieved the best overall performance among them. It recorded the lowest root mean square error or RMSE of 0.721 and the highest R square score, which is 0.892. This is our key finding. The ensemble showed the superior ability to reduce the prediction errors and explain the variance in the energy consumption data compared to any single model. We can gain even more insights by looking beyond the overall best R square score. While the ensemble showed the best overall generalization, the LSTM with attention model was a strong performer, achieving the lowest mean absolute error or ME, which is 0.347. This indicates its predictions were on average the closest to the actual values, likely due to the effectiveness of the attention mechanism. And conversely, the transfer model uh, exhibits the weakest performance with the highest RMSE and the lowest R squared value. This highlights the importance of hybrid and ensemble approaches, which effectively model complex nonlinear relationships. So, what do these improvements mean for the real world? Let's discuss about this. The real world impact of this enhanced forecasting ability is actually significant. It enables optimized energy management through real-time system optimization. Then it facilitates enhanced resource allocation for better planning of generation and distribution. And this leads to reduce operational expense by minimizing waste. And most importantly, it offers direct sustainability support for achieving global carbon neutrality. Despite these strong results, we acknowledge some limitations in our current work. The model's generalizability is limited to the shared GP3 dataset. The ensemble has a high computational cost actually, which may hinder real-time implementation. Again, the black box nature of deep learning models limits interpretability. This constraints defines the focus of our next phase of research. Our future study may focus on rectifying these issues, such as we may plan to pursue validation on diverse or real-world dataset. We may explore model compression techniques for efficient deployment, integrate explainable AI or XAI to address the black box problem. And finally, we may develop long-term forecasting models that incorporate external factors like extreme weather and holidays. In conclusion, I would like to summarize our main contribution. This study successfully utilized hybrid and ensemble deep learning models for precise energy consumption forecasting. We demonstrated a novel weighted ensemble approach, achieving a R score of 0.892. Then confirming superiority over traditional methods and end-to-end pipeline from pre-processing to deployment ready models. At last, it can be said that this study provides practical tools essential for energy managers to optimize consumption, reduce cost, and support global sustainability goals. The hybrid and ensemble approaches represent a significant advantage in energy management systems. I think in future it will be actually great helpful. And thank you for your time. I'm now open to any question.